$120 by PayPal, and 6 days later, you've got 35 belt buckles in your mailbox. And it really is that simple. You just send the money off, and then you've got belt buckles, and then you can have party time. Now, soldering them becomes considerably more difficult because we're trying to manufacture these not as kits, or we're trying to design them not as kits, but as something that can be mass-produced later on. Because even though all of you should learn how to do surface mount soldering, and in this audience quite a few will, it's not something that the general public uses, and that's the idea. We want like every bar in Knoxville to have neighborly belt buckles. So when you go in and they all start blinking, you can just scream out belt buckle and already have friends in that bar. So if you look closely at the image, you can see that on the bottom left of the chip, those devices have already been soldered. There's a capacitor at the top and a resistor beneath it. The capacitor is to make sure that the voltage to the chip is steady, and the current as well. While the resistor, it pulls up a reset pin to turn the chip on. At the top, you can see sort of gray paste over what will become LEDs of this belt buckle. The way that these are soldered is not with a soldering iron, but rather with tweezers, with a syringe that squirts out paste, and a hot air gun that blows out air hot enough to actually melt the paste into metal solder. So last night at HackDC, we set up and we were teaching a few people how to do surface mount soldering. And it's fascinating because you hand them the tools and at first they're shaking and nervous. No, it's so small, it's so small. But once they start squirting paste onto it and starting up the actual heat gun, as soon as the heat hits the first device, then surface tension of the solder actually lifts the device up and fixes any small imperfections in its placement. And then you remove the heat and you've got a perfect solder joint, and you realize how easy it is. And then suddenly you're grabbing the tweezers and pushing anyone who's trying to butt in out of the way. And it's loads of fun. And you're doing all of this just with tweezers and with a hot air gun. So it's the exact same process as a machine will do, soldering it with picking and placing. So it has a tape of these LEDs, and it picks them out of the tape, sets them down on the board, has a mask to place the solder paste in the right locations, and then it runs it through like a pizza oven. And I actually solder a couple of these with the convection Black & Decker pizza oven from Walmart. The same things work. But you can ship this design off to a factory, and you can order 1,000 of these tomorrow using only the descriptions that are in those CAD files and sending off a couple of reels of parts. Then you have to lay out the radio. And laying out a radio is a lot more difficult than I assumed it would be. Doing the CAD layout involves precisely positioning each piece, because at these frequencies, the copper itself changes the radio signal. So if you have a copper trace that's too wide or too long, or if you order a component in the wrong package, it can mess with the accuracy of the radio. You also have to purchase parts, and once you purchase parts in bulk, you're locked into a design. You can't go back and change things later. And then soldering is just as I described in the previous end, except some of these chips don't have pins coming out of them. They only have little pads on the bottom face. So using the hot air, you have to make sure that there's exactly enough solder underneath the chip. There are 3 types of radio antennas described by the data sheet. And when you're using a data sheet for a design, you pretty much just look at it and then you redraw it in your own CAD tool, and then it's part of your design. So you might do an antenna or a radio chip, and then you'll connect that to whichever microcontroller you need by the serial pins. But the 3 types of antennas involve a transmission line balun, which actually involves using the copper on the board as an inductor or a capacitor. Because if you have a ground plane on the bottom of the board and you've got a wire going over it, that's a capacitor. Because all a capacitor is 2 conductors separated by an insulator. And then you can actually calculate the capacitance by how thick the board is and how wide your copper is. That sort of stuff. Please don't call my phone. So then the discrete balun and the differential antenna are easier to make. They're easier to design because you're not using any such tricks. But they're not as neighborly, so we're going with the difficult one. When you get these components, you can't just solder them together as the schematic shows you, because you have to copy the actual copper pattern. You see the letters here, A through X. Every one of those is defined elsewhere as an exact width, and you have to copy that perfectly for the antenna to be properly tuned. That takes a while, and it's not terribly neighborly. Now, when you purchase parts, it's great being in America because they're already imported and easy to obtain. If you're in Switzerland or a country with import tariffs, it might be very hard to get them, or you might be forced to buy them in larger quantities than you would like. Also, if you buy the parts before you buy the board, you're locked into that design and you have no choice but to use the complicated antenna. And older chips are more expensive than newer chips with the same features, because when a chip is introduced, it's locked into designs, and then it can't be changed without hiring an engineer to change it. So factories will continue to manufacture old designs with the old parts, and that they're buying them means that they're still profitable. If those parts become cheaper, the customers get to make more money, but it doesn't result in significantly more sales. So when you're using chips, you should try and find recent designs of a trusted family. Like, get something old enough that all of the bugs are known, but not so old that you're paying $12 a chip when you can get a replacement for $4. For writing full custom firmware, it will lower your hardware cost, because you can specifically say, like, I'm using C, but I'm not using function calls, and write some crazy scripts to get around it and use a chip that's so small that it doesn't have a deep stack. But if you use TinyOS, well, it's not quite so efficient to your hardware. It's perfectly portable. You can debug before ever manufacturing a board, and it shortens your development cycle, because you can run the simulation of the PC and use all of the nice tools that they've built for you. If you were to do it custom, you would have to do power management and radio stack code yourself. You would also have to write this entirely in C and assembly without anything to manage events for you. Because in the raw, when you want to send a byte through a serial port, you first have to set up the serial port, and that involves on paper calculating exactly what the clock of that serial port should be, how it should be divided from the main clock. And then you're given an address. 0x0077 is the one of the first serial port. Every byte that you write there gets written out the port. And it's neat, because if you do it in assembly language, it's almost exactly the same thing that you see in disassembly. But it's terribly different from a PC, where you've got debugging symbols, and you can trap system calls, and you have different ways of identifying what's doing something important. Also, if your chip is active, it uses 1,500 times as much power as if it's in its lowest power mode. So of these 6 power modes, you want to be as low down as possible, recognizing that the further down you are, the longer it takes to wake up. So if you're in your lowest power mode, it might take you 20 milliseconds to start back up. And if you lose an event in that time, then you've, say, lost a packet or misresponded to something. But if you stay active all of the time, while you're perfectly able to respond to something, you consume a lot of power. There are serial buses which connect the chips on these boards. So the board itself is sort of like a computer network, in that you have, say, an I2C bus which connects the memory chips to the CPU, and then an SPI bus which connects the CPU to the radio. These can all be tapped in the same way that you can packet sniff on a network. You can inject packets, you can do all sorts of fun stuff. If you're building any secure design with this hardware, you need to consider these things. Now, for the party application, Josh, would you care to explain?
So each belt buckle will broadcast a packet. This packet is 128 bits, and it's just a random number. And when the packet is received by another belt buckle, that belt buckle will begin blinking and begin broadcasting that same packet as well.
Now, it's any packet that is received results in blinking and a rebroadcast. Further, a short timer is started to make sure that a broadcast occurs sooner than it would otherwise, because if you've seen a party before, it's likely that the party is still going on, and you're already spending all of this energy